In today's lecture, we are going to see the discussion of generation of gravitational waves. In fact, in our previous lecture, we have seen the theory of gravitational waves, where I have talked about its generation too. But in brief, I have told you that actually these gravitational waves are radiated, or gravitational radiation you can say, are radiated actually by the time varying quadrupole moment of mass. So this fact I have told you in that video will be explained in our forthcoming lecture. So this is the time when we will discuss how these gravitational waves are generated. In fact, as we have mentioned earlier, when the gravitational field is strong, there are a number of non-linear effects that influence the generation and propagation of gravitational waves. For example, you have seen the non-linear effects are significant during the last phases of black hole formation. The analytic description of such a dynamical changing space-time is impossible, and until numerical relativity provides us with accurate estimates of the dynamics of gravitational fields, under such extreme conditions, we have to be content with order of magnitude estimates. Okay? If you are not familiar with numerical analysis, then you have to rely on the magnitude estimate calculation. Okay. Furthermore, there are differences in the predictions of various relativistic theories of gravity in the case of high concentration of rapidly varying energy distributions. Okay. However, all metric theories of gravity, as long as they admit the correct Newtonian limit, make similar predictions for the total amount of gravitational radiation emitted by weak gravitational wave sources. That is, sources where the energy content is small enough to produce only a small deformation of the flat space-time, and where all motions are slow compared to the velocity of light. Okay? So how we can deal with the problem of generation of gravitational wave? I hope definitely you have an idea of the generation of electromagnetic waves. You have studied it in electrodynamics. So let us try to understand the nature of gravitational radiation by starting from the production of electromagnetic radiation. Okay? Electromagnetic radiation. You know, electromagnetic radiation emitted by slowly varying charge distributions can be decomposed into a series of multipoles. You know, if there is a charge distribution, let us say this, of arbitrary shape and size, and it is in motion, then you have definitely studied multipole expansion of potential earlier in your course on electrostatics. Okay? And in that concept, you have definitely discussed that a moving charge distribution is equivalent to monopoles. When the potential is expanded, that contains monopole term, dipole term, quadrupole term, and higher order term. Okay? So actually these electromagnetic radiations are emitted by the slowly varying charge distribution, and this can be decomposed into a series of multipoles. And you have also learnt that that the amplitude of the 2 to the power L pole, this is number of pole, where L you can see is either 0 or 1 or 2 and so on. When you take L equal to 0, then see 2 to the power 0, this will be 1. This represents actually the monopole. If you take L equal to 1, then 2 to the power 1, that will be 2. This represents actually the dipole. This represents two poles, that is dipole. If you take L equal to 2, then 2 to the power L will be 4, and this represents quadrupole. Okay. So 2 to the power L represents the number of poles. Okay. And when actually the amplitude of the 2 to the power L, when the amplitude of the electromagnetic radiation emitted by the 2 to the power L pole, that is a monopole, dipole, quadrupole and so on, then the expression for the amplitude contains a factor a to the power L, where a is a very small number, it is much smaller than 1. Okay. So if the amplitude is proportional to this factor a to the power L, then the value of amplitude will depend on the value of L. Okay. So let us see what will happen when we take the different value of L. If you take L equal to 0, okay, then the pole will be 2 to the power 0, that is 1. It means you are now talking about monopole. There is just a point charge. And in this condition, when we talk about the monopole, then you can see that in this condition, the strongest electromagnetic radiations are expected for this monopolar radiation. Why? Because in this condition, a to the power L, this will be equal to a to the power 0, and that will be 1, and this factor is highest. 1 is the highest value of a to the power L, because a is less than 1. When you will raise a power greater than this 0, its value will decrease. And as the amplitude is proportional to a to the power L, and when L is 0, then this a to the power L is 1, which is its maximum value. So in this condition, amplitude of the radiation will be maximum. And you know, intensity of a radiation is proportional to the square of the modulus of amplitude. So one can think that since amplitude will be maximum in case of monopole, so most intense radiation, most intense electromagnetic radiation will be generated by monopole. But the situation is not like that. The actual state of affairs is different from this fact. Why? Because you know, the monopole moment is simply the measure of charge. If Q is the charge, then this is actually the measure of monopole moment. And you know, charge is a conserved quantity. It does not vary with time. Okay? Since charge is a conserved quantity and charge is numerically equal to monopole moment, therefore no electromagnetic radiation is emitted by a slowly moving monopole. Okay? So monopole cannot produce electromagnetic radiation. Okay? I think you have clearly understood this point. If monopole is unable to radiate any electromagnetic radiation, then certainly the charge distribution for which this L is greater or equal to 1, that will produce such radiation. If you take L equal to 1, then 2 to the power L, you can see it is equal to 2, which represents 2 poles. So when L is 1, then you are talking about dipole. Okay? Actually, this electric dipole is the strongest source of electromagnetic radiation. This is the strongest source. Why strongest source? As you have seen, that amplitude will be maximum when L is 0, but monopole does not radiate. So next option for the least value of L is L equal to 1. And in this condition, the amplitude will be actually largest for radiation. And if amplitude is largest, then the intensity will be largest. And that's why we simply say that the electric dipole radiation is a strongest source of electromagnetic radiation. Okay? And after that, you can talk about the weaker magnetic dipole. Okay? Magnetic dipole. And electric quadrupole radiation. But can this dipole, can this dipole will produce radiation? Answer is yes. Electric dipole and magnetic dipole, these can emit electromagnetic radiation. And when you take L equal to 2, the number of poles will be 4, which is called quadrupole. And this quadrupole is also a weak source of electromagnetic radiation. So you can say that monopole cannot produce electromagnetic radiation or electromagnetic wave. Electric dipole is the strongest source of electromagnetic wave. And the magnetic dipole and the electric quadrupole are the weaker sources of electromagnetic wave. And as you will take very large value of L, amplitude of radiation will be so small, intensity will be so small, so that the radiation cannot be detected. And therefore, we simply say that that the pole which that the source which contains larger number of poles, that will produce actually very weak electromagnetic radiation. So we simply say that the quadrupole moment is a weak source of electromagnetic radiation. Magnetic dipole is also a weak source, but the electric dipole is the strongest source. And the monopole does not produce any electromagnetic wave. Okay. Now, one can proceed with a similar analysis for gravitational waves, and by following the same arguments, so that mass conservation, which is equivalent to charge conservation in electromagnetic theory, will exclude monopole radiation. Have you understand? If you are talking about the generation of gravitational radiation or gravitational wave, you can think this fact on the line of the generation of electromagnetic radiation. And as you have seen that an electric monopole cannot generate electromagnetic wave, in the similar manner, a gravitational monopole also cannot produce the gravitational wave. Why? Because when you say gravitational monopole, that means just a point mass, okay, a single point mass. And its monopole moment will be simply equal to mass. As in case of electric monopole, the electric monopole moment is equal to charge. Similarly, the gravitational monopole moment will be equal to mass. And mass is also a conserved quantity just like electric charge. And that's why, since this mass remains conserved, so a monopole cannot generate gravitational wave or gravitational radiation. Okay? You have seen that the electric dipole is the strongest source of electromagnetic radiation. But you will get surprised that the gravitational dipole cannot produce gravitational waves. This is a very contrast to that idea. Because the rate of change of the mass dipole moment is proportional to the linear momentum of the system. And linear momentum of the system is a conserved quantity. It remains conserved in a central force field, and therefore, since the gravitational mass dipole moment is proportional to linear momentum, and linear momentum of the system is a conserved quantity, therefore there cannot be any mass dipole radiation in Einstein's relativity theory. Okay? Gravitational dipole cannot produce gravitational wave. Okay? In fact, when you talk about the magnetic dipole, okay, for the case of gravity, the change of the magnetic dipole is proportional to angular momentum of the system. Okay? And as angular momentum is also a conserved quantity, therefore there will be no dipolar gravitational radiation of any sort. That is, neither a gravitational dipole can produce gravitational wave, nor the gravitational magnetic dipole can produce the gravitational wave. Okay? So lastly, you can say that the gravitational radiation is actually of quadrupolar or of higher nature. It means a gravitational quadrupole can produce gravitational wave. In fact, all gravitational quadrupole cannot produce gravitational wave. Gravitational waves are produced by the quadrupole, whose mass quadrupole moment actually varies with time. Okay? So I have mentioned that it follows that the gravitational radiation is quadrupolar or higher nature and directly linked with the quadrupole moment of the mass distribution. And as I have told you, when this quadrupole moment is time varying, then gravitational waves actually get produced. Now we will see these facts analytically in a mathematical way. One thing I would like to clear to you that actually the calculations made here is not step by step, because I have written some of the results directly, and so I will advise you remember those things, because the calculation of each and every step and each derivation will be a troublesome process, and that actually kills the essence of physics. Okay? That if you have a sufficient time, you make the calculation. Okay? So now let us see how analytically we can discuss the generation of this gravitational wave. In fact, as I have told you earlier, that these gravitational waves were predicted himself by Einstein when he had provided his general relativity. Then he had predicted actually gravitational waves, and he had also given the idea how these waves will be produced. Actually, this quadrupolar gravitational radiation is the idea proposed by Einstein himself. Actually, as early as 1918, Einstein derived quadrupole formula for gravitational radiation. And what is this formula? Actually, this formula states that the wave amplitude, which is denoted by the symbol Hij, is proportional to the second order time derivative of the quadrupole moment of the source. According to Einstein's formula, the amplitude of the gravitational waves produced by a quadrupole is proportional to the second order derivative of the quadrupole moment. You can see it here. This Hij, which is amplitude of the gravitational wave, this is given by 2 over r g divided by c4 qij tt double dot. See here. And of t minus r by c. Here mark it. Here this t minus r by c has been written in the argument of this quantity q double dot ttij. Actually, you know from electrodynamics that this symbol t minus r by c represents the retarded time. This is retarded time. And you have definitely studied electric dipole and electric quadrupole in your course on electrostatics. On that line, this qij tt. In fact, this quantity is the quadrupole moment in the tt gauge. When you say tt gauge, that means the transverse gauge, or you can say that the transverse stressless gauge. Okay, and it is evaluated at the time t minus r by c, which is actually retarded time. And how it is defined? This tensor is defined in this manner. This is actually the volume integral of rho times this much. Here xi and xj actually are the space coordinates, you know. R is the distance of the test point from the source. If here there is source of gravitational wave and you are making calculation at this point P, which is at a distance r from this source, then that r is here. And this delta ij, you know, this is the well-known symbol for Kronecker delta. And you know this Kronecker delta is 1 when I and j are equal, and this is 0 when they are unequal. D3x, this represents the elementary volume element. Okay? And the quantity rho in this expression, this is actually the matter density at point xi in the volume element D3x. Okay? So this is the defining equation of this quadrupole moment. Okay? Quadrupole moment. I have mentioned it here, all these things, delta ij, Kronecker delta, and it is 1 for I equal to j and 0 for I not equal to j. Okay? Actually, this result is quite accurate for all sources as long as the reduced wavelength, which is defined as lambda bar equal to h lambda divided by 2 pi, this is called a reduced wavelength, is much longer than the source size r. It means if you say that this lambda cut or lambda bar is much greater than r, okay, then this result which I have mentioned here, that is quite accurate under this condition. Okay. Actually, it should be pointed here that this result can be derived via a quite cumbersome calculation in which we solve the wave equation with the source term this T mu nu, which is actually the material energy tensor. Okay. But I have not made any calculation here. Okay. Actually, in the course of such derivation, a number of assumptions must be used. In particular, you have to take the observer located at a large distance r, which is actually much greater than this lambda bar. Okay, but I have not made such calculations. Okay, but that can be actually derived by using these ideas. Okay. Now, if you will talk about the power carried by this wave, which is also called luminosity. Luminosity, or you can say power carried by gravitational waves. Actually, using the idea of energy carried by gravitational waves, you may find the luminosity, which simply means power in gravitational waves. Actually, it is found that this luminosity or the power in gravitational waves is actually a function of the third order time derivative of the quadrupole moment tensor. So if you denote by this luminosity or the power by the symbol LGW, here the subscript GW is for gravitational waves, L for luminosity, that is defined by minus dE by dt. Actually, if this radiates energy dE in time dt, then in 1 second it will radiate energy dE by dt, and this is called luminosity. Okay, but I have put it here minus sign because this energy E is a decreasing function of time. So for getting the value of L positive, you must take here minus sign. And I have again directly written the expression. It is found that this LGW, which is defined by minus d by dt, making the use of the concept of energy, it is found that this is equal to 1 over 5 g to the power g divided by c to the power 5, and average or mean value of the partial derivative of Qij with respect to t of third order times same quantity. Okay, this is actually the average value of the product of these two. Okay, actually this result, which is defined in equation 3, this is known as quadrupole formula. Okay, in fact, it is seen that the quadrupole moment of a system is approximately equal to mass of the part of the system which is moving and times the square of the size of the system. Okay, so you can see that when we use this fact that this quadrupole moment is actually equal to mass of the moving part of the system multiplied by a square of the size r of the system. Actually, in this condition, the third order time derivative of the quadrupole moment becomes like this. This is del 3 Qij by del Tq. This is of the order of mr cube by t cube. This is not an exact expression, so I have written it here at the order of. And this is of the order of mv square by t. Actually, r by v, this is of the order of, r by t, this is of the order of v. So r square by t square is of the order of v square, and so I have written instead of r square by t square here v square, and one t is here, and this is written as ENS divided by t. In fact, in this equation, this v is the mean speed of the moving part. As you know, r by t has the dimension of speed. And this ENS, this is the kinetic energy of the component of the source's internal motion. Okay? And T is the time scale, or you can say time period. Instead of a scale, you may also call period. This is time period for a mass to move from one side of the system to another. But this time period, is of the order of r cube divided by gm. You can check it. When you discuss the motion of a planet almost in circular orbit, then you can find writing its Newtonian equation of motion, F equal to mv square by r, and you can get and this F is equal to g mm by r square, and this is mv square by r. Getting the value of b from here, you can find that time period, which is almost equal to a square root of r cube divided by gm. And once you know the time period t, its reciprocal will give you the characteristic frequency of the system. So this relation provides a rough estimate. This is not exact result. This will provide you a rough estimate of the characteristic frequency of the system. If it is nu, then this nu will be equal to 2 pi over t. 2 pi over t. Or you can say this not nu but omega c. Or you can say that nu is equal to 1 by t. Okay. So this result also gives an estimate of the frequency. Okay. Frequency can be estimated from here. Now, after getting this value for this t, and when you will substitute in equation 4 at the place of t here, then you will get the third order partial derivative of this quadrupole moment tensor Qij with respect to t. And when this will be used in this equation number 3, then after simplification, your result will become like this. LGW will be of the order of g divided by c to the power 5 times m over r whole to the power 5. And here you can write it in this manner. This is g divided by c to the power 5 m by r whole square times v to the power 6. V to the power 6. And this can be written in terms of the social radius of the source. This RSCH is the social radius. And if you will write the expression for this luminosity in terms of the social radius, you may write in this manner. This is C5 over capital G times RSCH over R whole square times V over C whole to the power 6. Because the social radius of the source is given by 2gm divided by C square. You know it. So when you will substitute it here, your result will be like this. Okay. Now see from this result. Actually, in general, this RSCH, this is always less or equal to R. Okay. And this V is also always less or equal to C. Okay. So if your aim is to get the maximum value of this luminosity, then you have to take the maximum value of this RCH and this V. Okay. So for getting the maximum value of LGW, we simply take R of the order of RSCH and V of the order of C. In this condition, the value of this LGW is maximum, and this maximum value will be simply c to the power 5 by g, because this factor will be 1. And when you will substitute the numerical value of C and D, which has a standard value, you get this is equal to 3.6 times 10 to the power 52 joule per second. This is a very large value. This is a very large power. So the maximum luminosity of a source which produces gravitational waves is 3.6 into 10 to the power 52 joule per second. Okay? Actually, this immense power is generally called luminosity of the universe. This is called luminosity of the universe. Now, this result actually explains why we expect the best gravitational wave sources to be highly relativistic compact objects. Because if the object is compact, then RSCH will be almost equal to R. Okay? And if its motion is highly relativistic, then this V will tend to C. In classical limit, V is much smaller than C. But if you are talking about the relativistic motion, V will tend to C. So in the case when the source is very compact, highly compact, then its size is of the order of Schaussel radius, and if its motion is highly relativistic, then V will tend to C. And therefore, in that condition, this luminosity will be maximum, and it is of the order of 10 to the power 52 joule per second, or 52 watt. Okay. Since this value is very, very large, therefore this is called luminosity of the universe. Luminosity of the universe. Okay. Now, actually, based on this formula, we derive some additional formula too, which provide order of magnitude estimates for the amplitude of the gravitational waves and the corresponding power output of source. First, using the above order of magnitude estimates, we can get a rough estimate of the amplitude of gravitational waves at a distance r from the source. Actually, it is seen that the quadrupole moment of a system is approximately equal to the mass m of the part of the system that moves times the square of the size of the system. Okay? And therefore, utilizing this fact, it is seen that this h, which is amplitude of the gravitational wave at a distance r from the source, this is of the order of g divided by c4 times E_s divided by r. And this can be written as, instead of this E_s, you can write epsilon times E_kin, kinetic. Actually here, this epsilon is a mere number whose value lies between 0 and 1. It means its least value is 0 and the largest value is 1. Largest value is 1. In fact, this epsilon is a measure of the asymmetry of the source, and it implies that only a time-varying quadrupole moment will emit a gravitational wave. Okay? You can see here, instead of E_s, I have written this much, where epsilon times this E_kin, This represents the fraction of kinetic energy of the source that is able to produce gravitational waves. It means the total energy of the source is not utilized in producing or in generating the gravitational waves. Only a fraction of it is responsible for the generation of gravitational waves. Okay? And it is clear from this result that this epsilon is a measure of the asymmetry of the source and implies that that only a time varying quadrupole moment will emit gravitational waves. If the quadrupole moment is not time varying, it is constant, then again gravitational wave will be not generated by a quadrupole too. But as quadrupole moment actually varies with time, so it is responsible for the generation of gravitational waves. Okay. For example, even if a huge amount of kinetic energy is involved in a given explosion or implosion, you can say, if the event takes place in a spherically symmetric manner, there will be no gravitational radiation. So I have told you that this epsilon is a measure of asymmetry. A huge amount of kinetic energy involved in an explosion, but the event takes place in a spherically symmetric manner, not asymmetrically, then no gravitational waves will be produced. So this asymmetry of the source is a root cause of the generation of gravitational waves. Okay. So this is all about the generation of gravitational wave, and I think you have definitely enjoyed this lecture. Okay, thank you very much.